Hi students. If you are having some issues understanding what's going on in the energy skate park simulation and the handout that we are using to investigate it, let me walk you through it here with this little demo. So part A is about thermal energy, and it says describe how a change in thermal energy of the system affects the motion of the molecules at the microscopic levels. And the motion of the skater at the macroscopic level. So microscopic being something you can't see with your eyes, right here below there's a linked friction simulation. And when it does say the skater and the motion of the skater, it's particularly talking about where the wheels meet the ramp. So when you click on this link, you can go to a simulation called the friction simulation. And here it's showing you a chemistry book sitting on top of a physics book. And this simulation allows you to grab one of the top book and drag it along here. And one of the things that you'll see in the thermometer here, as you do the dragging, you see the molecules moving faster, and they're getting hotter. And if you go too fast, you start to see molecules wearing away. And what's kind of expected for you to do with the handout for that part of the simulation, what's happening between the wheels and the ramp. And if you ever think about, if you've had some skates before, and you look at the skates after you've used them for, some weeks, skating around on the concrete, you see that they get worn away, and that's what you saw in this friction simulation. You put the chemistry book on top and grind it along the physics book, and over time your books wear on each other. So screenshot this. Take a screenshot of this. I'm going to go ahead and do that. I'm going to reset it, and I'm going to put the book on here. I'm going to screenshot it, and I'm going to go ahead and paste that in this document right here. Microscopic image at the left when he's up here at the top. Do you think there's more thermal energy and more friction when he's up here at the top or down here below at the bottom of the ramp? Well, I'm going to put that nice grinding microscopic model. I'm going to paste that there. Now, go ahead and look at that image, and you see, oh wow, that's a horrible image. But if you double click it, you should be able to crop some of that unnecessary stuff there. We can go ahead and crop some of that unnecessary stuff out. And you're going to see that there's more thermal energy in this part of the image than, let's say, when this person's at the top. You can go ahead and, if you do this wrap text, you should be able to move this around inside of this box. And remember, if you do something that you regret in one of these documents, you can always click this thing right here, which is undo. So that's what it's asking for in the microscopic model. That's what we're going to be seeing. We're going to be seeing wearing away of the molecules, and we're going to be seeing more thermal energy, and that's represented in this image. We can use here in the microscopic model for the left when the person's at the top. You see this little pie chart up here showing all the potential energy from when the skater's all the way up top. And there's very little thermal energy there because there's less grinding of the wheels on the ramp at that point. If you look at the energy, the second simulation here, the FET Energy Skate Park simulation, you open this one right here, and if you click home, it takes you to the intro, friction, or playground version of it. I want us to start on the friction one. Let's turn friction at normal, which is going to be in the middle. Put your skater on here and let your skater go up and down. You see the pie chart changes as the skater goes up and down between thermal, potential, and kinetic energies shown with these different colors. If we turn friction off completely and put the skater back up, he or she is just going to keep going up and down. It's going to be friction that inevitably stops this person from having this complete transfer of kinetic to potential energy as the person goes up and down. You'll see when you pause the person at the top, pretty much all of the energy of the skater's movements has been converted to potential. When you let the skater keep going and pause smack in the middle, pretty much all of the energy is kinetic. If there is no friction, at all times kinetic energy and potential energy are going to be conserved. At all times, kinetic plus potential energy equals the total amount. Notice I wasn't able to stop the skater perfectly down at the bottom here, but the kinetic bar, which is where the skater has the most kinetic energy down here at the bottom and is moving fastest, the kinetic energy is equal to the total energy. The only reason that this is a slightly bit lower is because this person's not smack at the bottom, at the very bottom. So imagine adding this little bit of potential energy to that kinetic bar right there, and kinetic and total would be equal to each other. I'm going to press play again and watch the kinetic energy and potential energy continue to swap up. So here is a better version of what I was just trying to show. Kinetic and total energy are almost equal to each other when the skater's at the bottom moving fastest, and then when the skater gets up here and stops, potential energy is now equal to the total energy. But at all times, if you take this kinetic bar and stick it on top of the potential bar, it will always equal the total. Watch what happens as the skater gets right here, where kinetic energy is increasing because the skater is getting faster. Potential energy is going to decrease. So potential energy decreased, kinetic energy went up, but still potential plus kinetic always equals total. Let's go back to the handout and think about what we should put here. So up here we're seeing the pie chart had very little has mostly potential energy, very little thermal energy. So if we were to use the friction, let's reset the friction simulation, put the book on there. From the skate park simulation and the handout, the skater's up here at the top with very little thermal energy. So how do we use the friction simulation to show very little thermal energy? Well, right here is what we're looking at. Very little thermal energy would mean very little heat registering on a thermometer. So let's go ahead and take a screenshot of that and paste it here in the handout. We'll have to do a little bit of cropping. So click it. Now we selected the picture. Double click it again to get these little black bars. You can crop your picture. Click off of it and it'll be cropped and focused on. To get your picture to be able to be moved wherever you want, you got to click the wrap text and you can move it to the center. So now we have the skater with a lot of thermal energy, and here's what's going on with the molecules. They're grinding away. And then when the skater gets back up to the top with little thermal energy, the molecules are going to be less rubbed away on the freshest part of the skater's wheel. And you'll see little thermal energy on the thermometer. Now, if we think about what the macroscopic model is showing, in the macroscopic model boxes, draw and describe the energy of the skater at the two positions. So if you're trying to draw and describe, you don't necessarily need to draw with these. You can, again, just take pictures. The best way to do that, I think, for this handout would be to go to the simulation and snapshot your kinetic potential and thermal energy images. So let's turn friction back up to normal, or you can reset it. Turn on your pie chart and your bar graph. It's up to you if you want to add the speed and the grid. I like to show as much information as possible when I do these things. Let's put the skater on there and press play. We're going to pause at the bottom. So, and now we have what the handout asked us for right here. In the macroscopic model boxes, draw and describe the energy of the skater at the two positions. So here's the bottom position. Here are the energies. So let's just screenshot that and crop down our box right there. So I'm going to paste that. Well, let's make sure I'm pasting in the right one. Oh, here's the right one. So we have, in our simulation here, we just took a picture of where the skater is at the bottom. And we have the bars that we can paste in here. So let's do that. And now we can focus in on two things. Focus in on making sure that we have that chart in there. Let's get rid of any other. Oh, I'm going to click back because I resized the picture without cropping it. So let's go back. Good. Double click your image. Now you can crop it to get the information you want focused on. Click off of it. Make sure it's wrapping text, and you can move it around wherever you need. Inside of the box. There. Now let's do the same thing for the other one, where there's the least thermal energy. I'm going to go ahead and let the skater keep going. Pause. So here, there is still some residual thermal energy. Now you'll see the thermal energy plus the potential equals the total. So the wheels are still pretty hot here. If you wanted to show this in the way that the program and the original author of the handout was looking for, you might want to just start it over. So let's reset, turn these things on, put the skater back, and let him go up one. There. So that's a little bit better. There's still some the wheels are still going to be a little hot. But you see here the potential energy is the highest, and potential plus thermal plus the eensy-weensy bits of kinetic are going to equal the total amount of energy. Let's screenshot that and go ahead and paste it in the document. So this is what the handout's looking for you to do. The bars are what we're really focusing on thinking about with this document and activity. I'm leaving the skater in the picture to help you think about what's going on there. Let's wrap text it, and there it is. I'm going to shrink it down just a little bit. And sometimes you might need, if this image isn't going exactly where you want it, you can always click on it and move it around with the arrows. And sometimes you might want to right click, copy it and cut it and paste it somewhere else in the box. That can often help you with your positioning. With that said, this part, probably don't need that part. This is a continuation of these boxes. So let's move on to part B, energy changes in the skate park system. I've already kind of talked you out through some of that, but here are your objectives. Differentiate between total energy and various form of energies in the system. So we have thermal, kinetic, and potential. Those are three that we've already seen. Explain how each model, bar graph, and pie chart shows the total energy of the system. And when it says explain, that's what we're going to be doing here in the reasoning section. Describe the energy changes in a system over time using both words and graphical representations. These are graphical representations here, and so is this here. Your pie chart, that's a graphical representation, and so are these bar graphs here. Going back to the handout, what objects are in your system? You have skater, you have wheels, you have ramp. What other objects to read there? That might be a good spot to stop to help you. Describe the system represented by the bar graph and pie chart. Explain your reasoning. Molecules of the wheels. And molecules of the ramp interact with each other and have friction. You could probably flesh that out more. I'm just trying to help you with this. I'm not trying to give you all the answers. Investigate the meaning of total energy. So at different positions, we have kinetic energy, thermal energy, and potential energy. The total energy, according to the bar graph, always equals what? So if you take this skater, put him back up at the top, anytime you pause this plus this equals that. Potential plus thermal equals total. If you put him here, see potential equals total. If you put the skater here, potential equals total. If you let him go, press play, pause it, kinetic plus potential plus thermal equals total. These are the things that you should be fleshing out in number 2. You should use different positions to prove this, both in terms of the bar graph and the pie chart. So taking some screenshots and pasting them in here would be what you're looking for with this handout. Continuing on to the mathematical model. Find a way to increase the total energy. Draw diagrams of the bar graph, and conveniently we don't need to draw. We can just use screenshots and crop down images for this. Find a way to increase the total energy. I just kind of showed you that. If you release the skater here, press play. Look at that, total energy is small. Put them up here, much higher. Could you do something else like increase the mass? Let's see here. So back to the handout. Draw diagrams of the bar graph. So you're going to be taking pictures of these and inserting them here before and after increasing the total energy. What did you do? You need to explain that here. Define the total energy of the system based on your observations. So describe those relationships. Describe the relationships that made up the total energy in your tinkering. Use the friction page to investigate the different forms of energy and the relative amounts when the skater is at different positions, top of the hill. So we've kind of done this in the walkthrough here. Finally, use trends in the table above to write a rule about the changes in the energy, including the total energy of the system. So a lot of this is going to seem redundant, meaning you've already done it. Including the total energy of the system as the skater moves along the track, use your own words. So finally, you're going to then go use your experience with the skater system to complete the table below. So you're answering questions about the skater's speed at A, the skater's speed at B, the skater's speed at C, and there you're not taking pictures, you're writing words here where it says describe. And finally, the graphical representation of energy. There you can take screenshots and crop them down. Take screenshots of the energy bar graph and the pie chart and paste them here. Remember to crop them down so they're small enough. Finally, you're going to go ahead and go on to part C, the mathematical model. At this point, though, I'm going to pause this and go ahead and allow you to get to work on it.